So in today's lesson, we're going to be learning about some different types of factoring, specifically how to factor what we call a difference of squares. So far in class, we've learned how to factor by removing the greatest common factor. We've learned how to factor simple trinomials, and we've learned how to factor complex trinomials and combinations of them. So today what we're going to be learning is a different type of factoring called factoring a difference of squares. So you'll remember that factoring is just simply the opposite of expanding. So when we factor, we take something that is a sum or a difference. In other words, we're adding and subtracting. And we take it and turn it into something where we're multiplying. So in order for us to see that, I think it's best to start by looking for a pattern. So what I want you to do is quickly take a look at the sets of examples that I'm showing you here, and I want you to first off see what you notice that they all seem to have in common. So what does each individual question seem to have in common? Well, I'm hoping what you noticed is that in every set of factors, I have the same first term and the same last term. I also wanted you to notice that one of the factors is a sum or an addition, and one of them is always a difference or a subtraction, right? So that in each case, I have that set of circumstance. So let's take a look at what happens when we expand this. So I want to remind you, well, what method, maybe you can guess, what do we call the method that we use to expand when we have two binomials? So I want to multiply out these binomials. What is the method that we use when we do that? Well, we're going to use the FOIL method. So again, we're not into factoring yet. I just want us to see if we can point out some patterns. So remember, when I FOIL, I multiply my first term in each bracket with each other, my outside terms with each other, my inside terms with each other, and the last terms in each binomial with each other. Okay, let's go ahead and do that. So I have x times x, which will give me x squared. I have my outside terms, x times negative 1, which will give me negative x, or negative 1x if you prefer. I have my inside terms, so my positive 1 with my x, which will give me plus x. And then my last terms, my negative 1 and my positive 1 together. Negative 1 times positive 1 will give me negative 1. So of course, what I can do here is I see that I have these middle terms that will cancel each other out. So I'm simply going to rewrite that. Let me just get my eraser function out here. And I'm just going to get rid of them. And rewrite that negative 1 right here. Okay, so I would like you to go ahead and do the same for the remaining set of brackets. It's not a bad exercise for you. And then we'll see how we do at the end of it all. Okay, so double check your expansions with mine and see that they match up. What I'm hoping that you noticed when you went through this exercise is that in each sets of expansions, that both the outside and the inside terms worked to cancel each other up. In other words, they were of opposite sign but of equal value, and so they added up to 0. That is what I'm hoping that you noticed. Okay, and so now I want to stop and remind you of what we talked about at the beginning of this unit, which is that, let me see if I can get rid of this. Factoring is the opposite of expanding. So in other words, what we have on the left-hand side is simply the factored form of the expanded form. So what we did was we expanded. So what we're going to learn today is, well, how do we take an expanded form, like x squared minus 1, and then convert that back to a factored form, right? So expanded form, we're looking at a sum or a difference. In this case, it's a difference because it's a difference of squares. And then we're turning that into a product in factored form. So what I want you to notice, what I want you to know about each of the expanded forms is that they all represent something that we call, let me see if I can get rid of this, a difference of squares. So all of these, let me see if I can write this out. All of these expanded forms right here are what we call a difference of squares. Now, well, what do we think of when we think of difference? Difference, hopefully you're thinking about subtraction. And so one way that you're going to be able to identify an expression as a difference of squares is that you're going to notice that they all, in fact, are subtractions. They're one term subtracted from another. Okay. Another thing that you're going to notice is that both of the terms in the expression are what we call a perfect square. So, for instance, and what do we mean by perfect square? Well, a value that is a perfect square is one that has a square root that is a whole value, not a decimal. So in other words, I know that x squared is a perfect square because it has a square root that's very easy for us to calculate, right? The square root of x squared, let me write that out. The square root of x squared is just simply x, right? So when I'm looking at a difference of squares, that first term is going to be a perfect square, and so is the last term. So 1, of course, I know is also a perfect square because the square root of 1 is at that nice whole number. It's a 1. And so if I go down my list, of course, in each question, there's x squared. So we know that each first term in this case is a perfect square. And also, if I look down my list, I can see that each of the second terms are perfect squares. For instance, 4 has a square root of 2. 9 has a square root of 3. And 16 has a square root of 4. We can even get the square root of y squared, which we know to be simply y. So each of these is a difference of squares, and I can recognize it as such. Again, because I'm going to see that there's a subtraction between the terms in the expression. The first value has a clear square root, and so does the second term in that expression. Now, another way for me to identify that this is a difference of squares is that I'm also only going to be able to see 2 terms in the expression that I'm asked to factor. So that's another clue that I have a difference of squares. So let's write some of that down. How to tell if it's a difference of squares? First of all, both the first term and the second term have whole number square roots. Except of course if we're talking about a variable, in which case we're just going to think of it as, a square root that is like a nice whole variable. Okay, the terms must be separated by a minus sign. They have to be a difference. So let's do some practice now to make sure that you can identify whether an expression is indeed a difference of squares. So let's have a little discussion around that. So I'm going to give you some examples. So in these examples, I want you to identify if each of the following is a difference of squares. So take a minute to look at each of these examples. I want you to write out whether it is or is not a difference of squares. And if it's not a difference of squares, maybe indicate why it's not a difference of squares. All right, so hopefully you've had time to work through these problems. I'm going to write out yes or no as to whether each of these is a difference of squares. So in this first example, x squared minus y squared, well, we just saw that example, so we should hopefully know that yes, indeed, it is a difference of squares. In the next one, well, let's take a look at it. I can see that 4 has a square root, and so does x squared. So the square root, I'm going to do that, I think, on the side. The square root of 4x squared is just simply going to be, well, the square root of 4 is 2. The square root of x squared is x. So 2x. So yes, that criteria is satisfied. 9 does in fact have a whole number square root, and it's 3, so that criteria is satisfied. The minus sign is separating these two terms, so I can tell for sure that this is indeed a difference. So it's a difference. Both the first and the last terms are perfect squares, so I'm happy to say that yes, this is a difference of squares. All right, let's look at the next example. Ooh, it looks like I went out of order there. Not to worry, no big deal. So when I look at this next example, I can indeed see that x squared is a perfect square. It has a square root of x. 25 is a perfect square because it has a square root of 5. So both the first and the second term in this expression are in fact perfect squares. So, however, when I look closely, I can see that it is not a difference. Therefore, this is not a difference of squares because it is not a difference. All right, didn't satisfy all the criteria. All right, let's look at the last example here. I have 5 minus x squared. So let's look at this. Well, right off the bat, I'm looking at 5, and I know that if I go ahead and I calculate the square root of 5, that's not going to give me a nice whole number. And so 5 is not a perfect square, right? So the answer to this is no, and that is because 5 is not a perfect square. In other words, it does not have a whole number square root. All of the other criteria looks like it has been met. It's a difference. It's got an x squared as its second term, but it does not have a perfect square in both of those terms, so therefore it doesn't qualify as a difference of squares. Hopefully you did okay with that, and if you have any questions about what I've said in this video, please feel free to send me a message through Google Classroom. All right, so let's get you to practice a little bit of this. So I'm going to demonstrate maybe the first example, and so on and so forth. I'm going to play this by ear and see how difficult the questions are, and decide how much to get you to practice on your own first. So let's try a first example here. I want you to look at A. I'm going to model how to do A, and then what we're going to do is I'm going to get you to try B on your own. Okay, let's give this a whirl. So when I look at this, first of all, it doesn't tell me that it is a difference of squares. It simply says factor fully. I have to recognize it as a difference of squares. So let's make sure that we do that. First of all, I need to make sure that I've removed any common factors. That is always a type of factoring that still holds true for every single factoring question. You need to go and look for that common factor and remove it if possible. Now, I don't see one here, luckily, so I should be good to go. So I can see my first term is a perfect square, and I see that my last term, 81, has a square root that is a whole number, so it is a perfect square. This is also a difference of squares. Therefore, I'm going to factor this as a difference of squares. Now, the way that I do that is very simple. I simply am going to prepare my two brackets, and I'm going to put an x in each of the first terms. So in other words, I'm taking the square root of the first term. In this case, the first term is x squared, so the square root of x squared is x. And then I'm going to take a look at that second term and figure out its square root, and I'm going to place one of those in each of the brackets. So the square root of 81 is, of course, 9. So I'm going to put a 9 in each of the brackets. So hopefully you're starting to recognize that this looks a whole lot like those patterns that we saw in my first little example. So hopefully you've already guessed what I need to do to finish my factoring, which is to put a sum or a addition sign in the first bracket and a difference or a minus sign in the second bracket. And there, I'm done. That is how you factor a difference of squares. So if I wanted to, I could go ahead and FOIL this to make sure that I end up with what I started with, right? So x times x gives me x squared. X times negative 9 gives me negative 9x. X times positive 9 gives me positive 9x. So the negative 9x and the positive 9x will cancel each other out. And then positive 9 times negative 9 will give me negative 81. So by expanding, I've checked to see that my answer is correct and I can move on. All right, so what I want you to do next is I want you to try B on your own and then we will check it out. So pause the video, try it, and then resume when you're ready. All right, so in factoring this, I've already gone through the criteria to make sure that it is a difference of squares. In fact, it is, and so I'm going to carry on with the solution. So I'm going to set up my two brackets. I'm going to put a plus in one and a minus in the other. And it doesn't matter which of the two factors contains the sum and which contains the difference. The order there doesn't matter. And so I'm going to take the square root of my first term, the square root of 144 is 12. So 12 and 12. Square root of a squared is simply a. And I'm done. Let's try some other questions. All right, so take a look at these two new examples. I want you to try them out using the criteria that we have outlined. Actually, maybe just try C, pause the video, and then we'll take it up. All right, so when I look at C, I've established that it does meet the criteria for a difference of squares. There isn't a common factor here to remove, so I'm not going to do anything about that. And so I'm simply going to set up my brackets. I'm going to put a plus in one and a minus in the other. Square root of 49 is 7, so put a 7 as my first term in each binomial. And then I'm going to take the square root, I'm going to do this on the side here maybe, the square root of 4b squared is going to be, well, the square root of 4 is 2, so 2. And the square root of b squared is b. So that tells me that I need to insert that in each of my two brackets as my second term. So this finished factored binomial, difference of squares rather, is 7 plus 2b times 7 minus 2b. And now I'm done. Okay, pause the video, try the second question, and then come back when you're ready to check your answer. All right, so in this case, I can see, I've already checked out to see that it is a difference of squares. So I'm going to proceed with my solution. So I am going to set up my two brackets. I'm just going to, for the sake of showing you guys, I'm going to show you, oops, I forgot. Let me just put my plus and my minus before I forget. So when I look at the square root of 25x squared, the square root of that is, well, square root of 25 is 5. The square root of x squared is simply x. Now I'm going to do the same thing for my 9y squared. The square root of 9 is 3. Square root of y squared is simply y. So that allows me to create the two factors that I need. So in my first term, the square root of 25x squared was 5x. So I'm going to place a 5x in each of the brackets. And then the square root of 9y squared was simply 3y, so I put a 3y in each of my brackets. And I'm done. Hopefully you did okay with that. And if you struggled with it, hopefully by breaking down that solution, you're able to see where you didn't quite understand and you're able to clarify that for yourself. If not, feel free to reach out to me via Google Classroom. So at first glance, question E does not look like a difference of squares. It doesn't look like it meets the criteria because we don't have a whole number square root for 12 or for 27. But what is the first type of factoring I should always attempt to do? I should always attempt to remove the greatest common factor. And I can clearly see that 12 and 27 both have they are both divisible by 3. And so I'm going to pull out 3 as a common factor and see what I'm left with, because sometimes removing the common factor allows you to see that you're not done your factoring. And in this case, we're going to see that I will be left with a difference of squares. So this example was meant to show you that even though something may not look like it's a difference of squares, the difference of squares might be hidden behind a common factor. So I'm going to pull out that common factor of 3. And so I'm going to say to myself, well, 3 times what is going to give me 12x squared? Well, that's 4t squared. And then 3 times what is going to give me negative 27? Well, that's minus 9. And so now what I'm left with, I can see in the bracket that what I am left with right here is in fact a difference of squares. And so I'm just going to continue my work. I'm going to carry my 3 down to the next line. And now I'm going to simply factor the difference of squares portion of this question. So 2 brackets. And I'm going to take the square root of this is business as usual, square root of the first term. Well, 4t squared has a square root of 2t. And so one of those goes in each of my brackets. I have a sum and I have a difference in each bracket, so plus and a minus. And then the square root of 9 rather, is 3 and 3. So now I'm done. And if I wanted to, I could go ahead and expand all of that and check my solution. Okay, I'm noticing that there's a typo in the next question. So what I want you to do is I want you to change this 2 for a 4. That's kind of messy. I'm going to rewrite it, I think, down here. So we're going to call this question F, and I'm going to say x to the power of 4 minus 1. All right, so let's take a look at this. So at first glance, this may not look like a difference of squares. So I'm going to just maybe point something out to you that maybe it hasn't occurred to you or whatever. So you'll remember that, I know that the square root of 9 is 3. And the reason I know that is because I said to myself, well, 3 times 3 equals 9, right? So then if I wanted to say, well, what is the square root of x to the power of 4? I know that that's actually just x squared. How do I know that? Well, because, I know that x squared times x squared, using my exponent laws, brings me back to x to the power of 4. So when I'm taking the square root of something like x to the power of 4, that's going to be x squared, because I know x squared times x squared will give me back what I started with. So this is in fact a difference of squares. I'm going to carry on with my solution here. So same as before. First bracket, second bracket, a plus in one and a minus in the other. So I'm going to say, well, what is the square root of x to the power of 4? Well, we just determined that that was x squared, so I'm going to put 1 in each bracket. What is the square root of 1? The square root of 1 is 1. So I'm going to put 1 of those in each bracket. Now, the thing is that I'm not actually done. So I always want to make sure, especially when I have higher exponents, questions with higher exponents, I want to make sure that what I am left with is not factorable. And I am keenly aware that what I have in this second bracket here is, you guessed it, another difference of squares, which means that I'm not done. I'm just going to clean up my workspace a little bit here, getting rid of some of this business. Here we go, and done. So I can keep going. So I can't factor this first bracket anymore because it's not a difference of squares. It's a sum of squares, and there's no way for me to factor that. So all I can do here is just drop that down exactly as is to my next line. But what I have to do for this second difference of squares, this guy right here, is create a second pair of brackets, right? So I know that this is a difference of squares. I'm just going to factor it as I did in all of the last questions, making one bracket a plus and one a minus. Square root of x squared is simply x. Square root of 1 is 1. Square root of x is x. Sorry, square root of x squared is x. Square root of 1 is 1. So now I have this oopsies. This thing right here is my factored form of my first yellow bracket here. That was a harder question. Maybe what I'll do is tomorrow as a practice, I'll give us another question that has a higher order exponent to it. But there should be some practice for you in your textbook around these types of questions, so that you can hopefully work through that. So please use the remainder of your 45 minutes to begin working through these questions here for homework. It looks like a lot. It's actually not. These difference of squares questions don't take a long time for you to work through. The only ones that might take you a little longer are ones where you need to think harder, but do your best within the time constraints to work through what you can. And we'll check in tomorrow.